Hello everyone, it's Jeremy from AI Expedition. I recently posted a video where I showed you how you can use AI to improve the quality of your images. If you haven't already seen that video, I've included a link in the video description. Hopelang, with a cool profile picture, asked me to explain the intuition behind those models. So today I'll give you some background and intuition on how those models work by going through my TensorFlow implementation. The link to the code is in the video description. As I go through the code, I'll talk through the reasons for some of my implementation details. Just a warning before we begin that this video is going to get quite technical. Alright, let's begin. The models I'll talk through are called SRResNet and SRGAN. Both of these models fall under an area of research called image super resolution, and they were both introduced in a paper called Photorealistic Single Image Super Resolution using a generative adversarial network, and it was authored by these lovely people over here. I've opened up the file, train SRResNet and SRGAN. This is the code that I used to train both of the models. Before we talk about the models, I'll go through the data preparation. We have to show the models some examples of low-res and corresponding high-res images. This is pretty easy to do. We just need some high-res images, and we can resize them to get low-res images. In the paper, they mentioned that they used a random sample of 350,000 images from the ImageNet database. The ImageNet dataset is 150 gigabytes, and not all of the images are high quality. So I opted to use the div2k dataset instead, which contains high quality images in 2K resolution, and it's only 4 gigs. This dataset is specifically designed for image super resolution and has different types of low-res images that correspond to the high-res images. If you're interested, you can read the descriptions of the different downscaled datasets on this website, which I'll link in the video description. We'll use the bicubic X4 dataset since that's the type of downscaling that the paper uses. I haven't trained models for the other downscaling datasets, but I have made it easy if you'd like to train with other datasets. You just need to change this dataset key. I've just written some code that handles downloading the dataset from the div2k website if you haven't already got it. Depending on the dataset you choose, it will determine the scaling factor. For example, any of these X2 datasets uses a scaling factor of 2, and similarly, any of the X4 datasets uses a scaling factor of 4. So that's what this piece of code does. If I choose an invalid dataset, it will give me a list of the available datasets. I'll go ahead and stick with bicubic X4. Now, we can't just send in whole images to the network, because some images could be really big and the GPU could run out of memory. So we crop patches out of the images and send those to the model instead. In the paper, they use high-res crops of 96 by 96 pixels. So we do the same. Here, I'm just defining a list of mappings to use during training. This first mapping takes crops of 96 by 96 from the high-res image and the corresponding crops of the appropriate scale from the low-res image. For example, X4 means that the images have been downscaled by 4 times, so the low-res patches will be 24 by 24 pixels. Then, something that's mentioned in a lot of these super resolution papers is data augmentation by horizontal flipping and random rotation. That's something that's not mentioned in this paper, probably because they have tons of data since they're using ImageNet, but I've included it since our dataset is a lot smaller than ImageNet. Finally, with a lot of these image super resolution projects that I've seen, I found that they don't handle upscaling JPEG images well. They just seem to increase whatever noise was in the original JPEG images. Originally, when I trained these models, I found the same problem. So to counteract this, I've made my image super resolution model train with JPEG noise, so that if there is JPEG noise in the input images, it learns to remove that noise. After that, I just create TensorFlow dataset objects that will allow me to train the models. Those dataset objects are nicely optimized to cache the images in the dataset to make things train faster. It also creates a streamlined pipeline to perform these train mappings. If you're interested in that, you can go ahead and read through the code in the div2k loader file, but it's not super exciting stuff. Just optimized data preparation. Now, we finally get to the part where we can train the SRResNet model. First, we have to define the SRResNet model, and I've done that in the build SRResNet method by following the architecture given in the SRResNet paper. The SRResNet model is a convolutional neural network, or CNN for short. If you've worked with CNNs before, You might have noticed that as you go deeper into the network, the width and height dimensions tend to decrease. This is because we usually use pooling layers or apply filters with strides greater than 1. But for image super resolution, we don't want the width and height dimensions to decrease. In fact, we want the opposite. So the SRResNet model doesn't use any pooling layers, and it only uses strides of 1 and always uses padding. Now in the code, I've just made sure that when someone builds this model, they can only choose upsamplings of either 2, 4, or 8. Those are generally the scales you'll use when working with image super resolution. We start by defining an input layer, and we're saying none none 3 because we want to be able to take color images of any height and width. This is a fully convolutional network, so we're able to do that. Those input images contain pixel values between 0 and 255. In the paper, they scale the values of the input images between 0 and 1. So we do the same. I believe they do the data normalization outside of the network, but the reason that I'm doing it inside is just for convenience. Otherwise, when someone uses the model, they'll have to remember to normalize any image before they send it into the model. And if they forget to normalize, they could get some strange results. This way, they can never forget to perform the normalization step. Now, let's get into the actual model architecture. It starts by sending the input image through a convolutional layer that uses 64 filters of size 9 by 9. So we've got exactly that, and since we don't want the height and width to reduce, we're using padding is equal to same. Then we send that to a parametric ReLU function. As a side note, I'll explain what a parametric ReLU is. Neural networks use nonlinear activation functions to learn complex mappings. In our case, we're trying to learn a mapping from low-res images to high-res images. In practice, people have found that the ReLU activation function tends to work well. But the problem is that it causes a lot of dead neurons inside of your network, because every number less than 0 will simply be mapped to 0, and the parameters attached to those neurons won't be updated. So, instead, people came up with leaky ReLU. Instead of setting values less than 0 to 0, we set the values to some predefined constant fraction of themselves. But then people said, hey, instead of choosing this constant fraction, we should let the network figure out a good value on its own. And that's what a parametric ReLU is. Now, usually it would create a separate parameter value for every value that was passed into the layer. But here we're saying shared axes is equal to 1, 2, meaning that we're sharing the parameters across the width and height dimensions. So we're only creating one parameter per channel, and since we're using 64 filters, there are 64 channels, so it's only adding 64 parameters. The output of this PReLU layer is sent to multiple places, so that's why I've also defined another variable x_1, because we'll make use of these values later. First, we send these values as input into what's called a residual block. There's nothing fancy here, we're just grouping common operations and calling it a residual block. That's because all of the operations in each of these blocks are the same. Inside of each of these blocks, we have a convolutional layer that uses 64 filters of size 3 by 3. This is followed by a batch normalization layer, followed by a parametric ReLU, and then another convolutional layer with the same settings, and then another batch norm. We take this batch norm and perform an element-wise sum with the input of the residual block. So that's the second time that the output from this parametric ReLU is used. Then we continue stacking residual blocks one after the other, each time sending the output from the previous block as the input to the next block, and performing an element-wise sum between the block input and its final batch norm layer. The purpose of all of these residual blocks is to extract features from the input image. Historically, for image classification tasks, people have figured out that some of the earlier layers in a CNN learn to detect low-level features, like maybe lines going in a certain direction, and later layers in a network learn to start detecting shapes like squares and circles. Then, as you go deeper, the layers learn more and more complex structures and eventually learn to recognize entire object classes. Now, I'm not 100% sure that this analogy holds for image super resolution, but you can see in the paper that adding more residual blocks does seem to produce better images. Of course, it comes with the trade-off that your network will take longer to process images. In the paper, they settled on 16 residual blocks as a good compromise. So you'll see the exact setup of those residual blocks here in the code, and then this loops is just responsible for creating all of them. After all of the residual blocks, we have another convolutional layer and a batch norm layer. And then we see the third time that the output from this parametric ReLU is used. We perform an element-wise sum of that with the output of this batch norm. And up until this point in the network, the height and width dimensions haven't been changed at all throughout the network. But now we reach a new type of block, and I'm going to call this block an upsampling block because it increases the width and height dimensions. And it does that by using a convolutional layer with 256 filters of size 3 by 3. So that's 4 times the previous number of filters. And now we have something that you may not have seen before, called a pixel shuffle layer. What it does is take values from the channel dimension and sticks them into the height and width dimensions. In this case, it says pixel shuffler times 2. So it's doubling both the height and width and then dividing the channel dimension by 4. Let's say we have our activation map of shape 24 by 24 by 256. We divide the channel's dimension by the block size squared. In the diagram, it says pixel shuffler x2, so the block size is 2. This gives us 256 divided by 4, which is 64. So we divide the channels into groups of 64. And then, since the block size is 2, we double the width and height dimensions and fill in each of these 2 by 2 blocks with values from the other channels. So after this pixel shuffle layer, the width and height have been doubled, and we send those values through a parametric ReLU. And this is all followed by another upscaling block. So after all of that, the original widths and heights would have been multiplied by 4 each, and we would have 64 channels. Now, since color images only have 3 channels, they ended off with a convolutional layer that uses 3 9 by 9 filters. So this entire network produces an image where the heights and widths have both been upscaled by 4 times. And that's the architecture of the SRResNet model. The code that I've written is just a bit more general, because instead of hard-coding 2 of these upsampling blocks, I'm dynamically creating the number of upsampling blocks based on the scaling factor. So that's the model creation done. Over here, I'm just creating a checkpoint and a checkpoint manager that will make my training a bit more resilient. If my training dies halfway through because of a power outage or whatever, I want to be able to continue training from where it left off instead of training from scratch. I'm also defining a learning rate of 10 to the minus 4 with Adam, just like they did in the paper. They also mention that they train for 1,000,000 update iterations, and all that means is that they're using 1,000,000 training steps. So I'm just defining the training steps and the number of training steps per epoch, and then feeding the data into the model to train it for the required number of steps using the mean squared error loss and the PSNR metric. It took around 10 hours of training on my GTX 1080 Ti GPU to train this SRResNet model. This code over here just saves the weights after the model has been trained. And just like that, we would have implemented the SRResNet model. So let's move on to the SRGAN model. SRGAN is short for Super Resolution Generative Adversarial Network. The idea behind a generative adversarial network, or GAN, is that you have 2 networks competing against each other. In this case, we have a generator that tries to produce high-res images and a discriminator that tries to determine whether or not an image is an original high-res image or if it was created by the generator. So the generator tries to fool the discriminator, and it gets better and better at doing that. But then the discriminator is also getting better and better at detecting these generated images. However, the discriminator actually helps the generator by telling the generator where it went wrong. In the paper, they use the SRResNet model as their generator, and the architecture of the discriminator is pretty straightforward. It's just an image classification CNN, and it's made up of really standard network components. Now, on top of that, this paper also introduces a new content loss to measure the similarity between the generated images and the expected high-res images. Previously, we compared the images pixel by pixel using mean squared error loss, but comparing images pixel by pixel isn't necessarily the best thing to do. I mean, do you really care if the whiskers of this baboon are off by a pixel or 2? You probably don't care about that as much as having a realistic, high-resolution image of the baboon. So instead, we compare the activation maps inside of another pre-trained network called the VGG19 network. So we're using a mean squared error loss between the activation maps of the high-res and generated images. And although the mean squared loss is still performing an element-wise comparison, The activation maps have a larger receptive field than raw pixel values. This is because the VGG model was trained using pooling layers. Here you can see the difference when training with different VGG layers as opposed to training with pixel-wise loss. So here's the previous SRResNet model that we trained. Here's SRGAN trained with pixel-wise loss, and then SRGAN trained with different VGG layers. So we're including this VGG network here so that we can get the activation maps. The binary cross-entropy loss is going to be used for the generator and discriminator training, and this mean squared error will be used for the new content loss. Now in the paper, they trained this model using a learning rate of 10 to the minus 4 for 100,000 training steps, and then they reduced the learning rate to 10 to the minus 5 for the next 100,000 steps. So that's what we're doing over here with this piecewise constant decay. We use the same learning rate for the generator and the discriminator, and again a checkpoint and checkpoint manager for resilient training. Now for this model, I'm going to train it using the TensorFlow gradient tape instead of Keras. To me, it's going to look a lot neater than trying to shove 3 different networks into a Keras model. If you've seen some GAN networks written in Keras before, it's kind of confusing because you have to set the trainable property of the subnetwork to false. If you haven't seen it, don't worry about it, but it can be confusing. So instead, I'd like to just outright avoid all of it and use the gradient tape method instead. If you haven't seen the gradient tape method before, you usually create a train step function with its here function decorator, and then you create a scope with a TensorFlow gradient tape, and this helps you to get the gradients of your loss functions with respect to the variables inside of the scope. So here I've got this content loss, which is calculated by taking the generated and original high-res images and sending them through our perceptual VGG model. We scale those activation maps by dividing by 12.75 as done in the paper, so that they're on the same scale as the original pixel-wise mean squared error loss. Then we compare the feature maps using mean squared error. The generator loss is calculated based on the number of times that the generator fooled the discriminator. In this fancy equation, all of this is just the generator output, and it is sent to the discriminator. And then this minus log comes from the half of the binary cross-entropy loss, where the target variable is 1. So that's what's happening in this piece of code over here, and we use the content loss and the generator loss to calculate the perceptual loss as done in the paper. The discriminator loss is calculated as the binary cross-entropy loss for when the discriminator classifies between the generated and original high-res images. We get the gradients from our gradient tapes and then apply them using our Atom optimizers. All of this represents a single training step, so we chuck this into a for loop and repeat it for the required number of steps. I've just added in some code to monitor the losses every 1,000 training steps, and it also outputs an image in the monitor folder so that I can see how the validation images are being affected as training progresses. Running this training block took around 7 hours on my GTX 1080 Ti graphics card, so adding that to the 10 hours for the previous model, that's around 17 hours of training time in total. If you plan on training these models on Google Colab, it was taking between 2 to 3 times longer for me, and also your sessions might time out. So I suggest saving your checkpoints to your Google Drive. So here in the SRResNet model, you would do something like /drive/. And don't forget to change the checkpoint folder for the SRGAN model as well. Also, modify the code to save the weights to your Google Drive as well. This should make your training resilient, so that even if Colab kicks you off, you can resume training from your last checkpoint. That's all for this video. Thanks for watching. If you're interested in learning more about AI, be sure to check out my website, aiexpedition.com.